Calculus students are amassed and ready for wisdom. Wisdom. Good morning, team. Got some beautiful wake up music in the background there. I see you waking up, Thomas. Those eyes are slits. Nice. Thank you for showing up face to face, the 5 of you. I like to see your faces. So, 6. Hi, Gabriella. How are you today? All right. Something awesome to show you today. As I mentioned a little bit yesterday, the sort of the thrust of the book is you have the basic idea of what an integral is, and substitution being a fairly powerful technique. It's one of only 2 that you need to know. You can do a lot of things, and so this book chooses to take the approach, let's go do a bunch of those things. So chapter 6 launches into a bunch of cool stuff, and it really starts today. So let's do it. Let's get a screen shared. I'm trying to try plugging in my iPad today and see if it links a little better. So 6.2. Cool stuff. Well, I guess I should turn my music off, shouldn't I? Pains me to do so. 6.2 is area not under a curve, but between curves. And as I mentioned before, finding the area under a curve is sort of weird. Like, why would you, in the real world, why would you ever want to know the area under a curve? Well, you did an assignment last night. They gave you application for that, switching from rate of change back to the kind of the amount itself. So that's not a physical area, but when you graph it, it's represented by an area. But now we're going to kind of move to something that really is more geometrical. We're going to start, just to arouse your anticipation, we're going to start with, shapes like this. Like I could say, hey, what's the area under that? Oh boy, it's lagging behind. You don't see that yet. How do I fix this? What is going on? Any of you guys good at computers? Do you think it's a good idea if I shut my computer off? Like I drew what you just saw right there. I drew it like 5 seconds ago, just forever ago.
I mean, when's the last time you shut your computer off?
I shut my iPad off yesterday when we were having trouble. I haven't shut my computer off in a while. Is that worth trying at some point?
I mean, yeah, I usually shut my computer completely down at least once every couple days.
Yeah, maybe I'll try that when we get to a stopping point. So we're going to start today by finding that area right there, which actually isn't a very big jump from what we already know how to do mathematically. So now you're starting to sort of look at shapes that exist in the world and be able to define them. It's not area under a curve down to some arbitrary x-axis. It's just the area that you see. And so we're going to find the area between 2 curves. And then in later chapters, we're even going to take that shape, and this is very exciting. We're going to take that shape and spin it around. Seems like a lousy drawing. What's wrong with that drawing? Oh, there we go. We're going to spin that shape like around the y-axis and actually create a volume. And we're going to find that volume too. And so, we're really going to kind of take off here. Now, fortunately, the integral taking will be within your scope. Like it'll just be substitution or maybe just a straightforward power rule. That's kind of the 2 things you can do right now. And so this is kind of neat. And I'll give you a project about this and some, applications and all kinds of stuff. But But let's start off with the area between curves. So let me see. I'll just give you this. I'm going to go graph this in Desmos. You might want to do this as well, but I'm going to make one curve. Let's see. Let's even be a little fancy and call this f1 of x. Negative 1/4. I'm going to go graph this in Desmos plus 2x plus 1. And our second function is a line, negative 1/2 x plus 5. And you should recognize that as a parabola and a line. And so that's going to make something like that red shape that I just described. Except for the parabola, you might expect is upside down since it has a negative a value, and the line has a negative slope. And so, what's that going to look like? Well, let's go take a look. So Desmos seems to be reacting relatively quickly. Let's see, do I care? What do I call this? I think I don't see any reason I can't call it y for right now. So y equals negative 1/4 x squared plus 2x plus 1. And I can get away with the same exact language, negative 1/2 x plus 5, negative 1/2 x, lost my 2, plus 5. So we're talking about the area between those two curves. Now, you don't need to know anything new to do this. So I want you just to think about that for a second. Why do you not need to know anything new to do this?
Because the integral is the area under the curve. So we can take the area of the big one and subtract the area of the smaller one.
Yeah, does it make sense? We know how to find the area underneath the curve right now. So if we found the area under the red curve, which goes all the way down to the x-axis, and then we found the area of the blue curve all the way down to the x-axis and subtracted them, wouldn't that give us the area we're after? Nothing new. What did I do to make this problem really nice for you? What is very important to know that you know just from this graph?
We can use power rule.
Yeah, nice, easy equations. It's just going to be power rule. What else do you need to know about the integral?
We need to know where the two functions are equal to each other.
Yeah, does it make sense? You need the limits of integration. Like I didn't give you this. I could on a test or in an assignment just say, hey, find the area defined by the space between these two curves. And in this case, that's not ambiguous. And so it's like clearly they enclose a region there. But you would have to know where they intersect, as Bale said, because that's what tells you the limits of integration. And notice it's really clear where they intersect. They intersect
it looks like 2 and 8.
Yeah, 2 and 8. And notice we don't even need to know why, but they intersect at 2 and at 8. And so there's our limits of integration. And that was nice because those don't have to cross at nice numbers. You may remember from Math 111 that you had to find the intersection of two equations. And I just as a side note, could you set those two equal to each other? They have the same y value where they cross. So could you set them equal to each other and solve it? If you did, can you already see that it would be a squared equation and have two answers? And graphically that makes sense because there's two places where they cross. And thanks to the graph, if I did that algebraically, I better get 2 and 8. To the extent that you don't, that you're growing in your algebra knowledge, if you don't think that's totally easy, I don't even need to do that, then you should do it. Stick it in the quadratic formula, set them equal to each other, just mess around with it. I mean, you want to be eminently capable of doing that. Let me show you a couple of cool tricks in Desmos. Maybe I'll save that for a little bit. Let's just get this thing going here. Scoot. Get smaller. Why can't I move you? There we go. Let's go to projector mode. And what I'd like you to do is just, I don't know, get ahead of me. Like take a second and do this yourself. You don't need to know anything new. while I take it over and make a nice drawing of it and so forth.
Because of the shape of this too, couldn't we use geometry for the -1/2 + 5 to find that area instead of having to take the integral?
Good question. I'll let that hang for a second. What do you think about Eve's suggestion? Do we actually have to use an integral to take this?
I know for 1/4 to take the integral of -1/4 squared, you have to use the integral, but I'm talking about for -1/2 x + 5.
Yeah, good job. She's right. She clarified her statement. You can find the area under the blue line just using geometry, but you would not be able to find the area under the red parabola without using calculus. So you're exactly right. Now, you may agree that since the integral is so easy to take that it might even be easier to take the integral. I guess that's arguable. But no, I mean, even on a test, I don't care. So that's apparently the 0.24, and this is apparently the 0.81. So this is just kind of cool. If I say the area under F1 times dx, like in other words, I'm finding the area under the parabola, and that's the advantage of naming them F1 and F2. It's just kind of a cool way to write things down. You should say that's totally easy. I know what to do. That's the integral. So I think I'll even just take it. So that'd be -1/4 x cubed. But then I would divide by 3. And since there's already a 4 there, that would make it a 12. The 2x would become an x squared. The 1 would become a 1x. Evaluate that at 8 and at 2.
So are we trying to find the difference between the two areas?
Exactly. So what we're getting, and maybe you have some ideas and thoughts right now, what we're getting is that area right there. Uh-oh, it's lagging way behind again.
And then you would subtract the other area from that, right?
That's exactly right. So
Okay, threw me off with the quadratic part. I was like, wait, how's that going to help me?
Exactly. So I just want you to see this because, and I purposely showed you a minute ago that we're going to go 3D with this at some point because you need to be really good at picturing this. You got to be able to see this because when we go 3D, it's going to be tough because you can't have a 3D drawing. You can only have a 2D drawing. And so you got to be able to conceptualize what you're doing here. And you got to make sure you see this is like, this is easy. This is not hard. So
Yeah, that makes total sense. It's not really that hard to do.
no. So some of you beat me to the punch. What's the answer to this to save time? I don't want to type it in my calculator. It's going to take forever. If you get it wrong, fine, we'll fix it. But somebody tell us what you think the answer to that is. All right, I am doing it since no one's telling me, so I will waste our time.
I think it's 9.
I like that. I think it's 9. Not sure. Good for you. Haven't checked your work. Anybody agree with that so we can move on?
I'm still typing it in my calculator.
No worries.
My bad. 9 is for the whole thing. The first one I got 24.
Got it. Yeah, I got 29 and a third minus 5 and a third for that. So I got the same thing. So I got 24. Then you move on to, again, I'm just trying to give you time to picture this. Now we want this green area, which would be the area under the F2 dx graph. That's an easy integral to take, or as Eve said, just do it manually. You get negative x squared plus 5x, also evaluated at 8 and 2. If Martin is right, thinking the answer is 9, you got 15 for this. Is that true?
Yeah.
Okay. So if I go back then, the red area would be 24 minus 15 equals 9. And again, it's like, it's squares. I mean, I hate books that say square units. That just seems weird. But you know, it is an area, so it's not like the graph is centimeters, but I don't know, it always bothers me to write down naked numbers, as they say. And again, it's kind of fascinating. It's still, I hope it still amazes you that the answer to that is 9. Like, it's curved. It's literally saying if you took 9 squares that were 1 centimeter by 1 centimeter and got out a pair of scissors, that you could perfectly fill that space up there. It's almost hard to believe, isn't it?
I'm at the point in math where nothing surprises me.
Yeah, the order and the beauty of it is unbelievable. I mean, we're a long way from Kansas from when we started this class, like back in the fall term, taking integrals and derivatives, and it's like how we even got here. But it's cool that one of the things I like about these questions is our feet are still on the ground. Like, you could draw that for anybody and say, does that have an area? And they'll go, yeah. I wonder if there's a way to figure it out. And the answer is yeah. You got 600 hours. I'll show you how. Now, so does the logic that you're subtracting make sense? Like, this is extremely important. You should not be subtracting because you found a formula in the book that says to subtract them. You should look at the picture and go, well, of course you're subtracting. Duh. So here's my question. One of my questions. I wonder if, and notice it's kind of important that this is the top graph. Like, you got to know which one's the top. Does it make sense if you did it backwards, you get -9? So you got to make sure to subtract the top one minus the bottom one. And so in this case, if I take -1/4 x squared plus 2x plus 1, and I subtract from it -1/2 x plus 5. Remember how, and again, I'm lazy because I didn't put dx's in there. Do you remember how we said, we love plus and minus signs? Do you think it would be true? Do you think it's possible then that you could just do it this way? I mean, since integrals and derivatives don't care about plus signs, do you think we could just stick it all in there together and get the same answer? Should that work?
A part of me wants to say no. Just because, first of all, if you're adding it in there, isn't that not right? Because you said add 1/2 and you got rid of the negative sign as well.
Yeah, I said add just because it was minus and minus. So it's kind of minus
Okay.
everything. So I did make an algebra mistake, although
So you're suggesting to subtract the one integral from the other, right? And then combine them all together.
Yeah, notice, as Justin said, like if I collect this all together now, then 2x plus 1/2 would be 2.5 or 5/2 x, and then 1 minus 5 would be -4. Like, if this works, or if it worked, or if it was worth trying, that kind of, like, that would save me a little time, because notice I don't have to find, it's kind of like I don't have to find the area under the line now. I just have to find the area under a different parabola. But of course, that's a different parabola. And, if you just look at this problem all by itself, it would be some kind of a parabola that whatever looks like that. And I'd be sort of finding that area right there. So the question is this area equal to that red area up there? Like, it certainly isn't going to look like it. You understand what I mean?
I'm gonna say it doesn't feel like it should, but it probably is. With
Yeah, I mean-
your lead up into it.
Yeah, I'm sure we need to spend 10 minutes and go, no, it doesn't work. But notice that's one of the rules. Like it sort of has to work. That's kind of the issue here. It actually kind of has to work because really when you take an integral, you're doing every one of these separately, aren't you? Like you're taking the integral of 1/4 x squared and you're getting negative 1/12 x cubed. And then you separately say, okay, now what's the integral of 2x? Like plus and minus signs are separate. You're doing them separately. So, you know, why does this have to be two separate integrals? Couldn't it just be under one? And then before I take the integral of all 5 of these terms, if there's some that collect, why not collect them? Now the weird thing is you don't get the same, you get the same area, but you don't get the same graph. Do you understand that? Like it's not the same graph at all.
Well, it's kind of like when you substitute in u and then you look at the graph that you get in
Exactly.
the u version. It doesn't look anything like the graph from the original function, but the area will equal the same.
Couldn't be said any better. Let's go.
Wait, so I have a question.
Go ahead, Eve.
What about the limits for this equation?
That's
Like, I know the limits are the same for both of them, but does that mean they change at all?
Yeah, good question. In other words, this problem back here, if I go back and add them back in, was from 8 to 2 and from 8 to 2. And so part of me wants to say, well, it's the same limits. So, you know, couldn't I just combine them together and go 8 to 2? But again, for Eve to stop and question, like, you know, is it the same limits? Maybe not. Well, let's just try it. I don't know. Let's see if she's right or if it actually works just like it is. So, you know, we didn't cheat, but a lot of us looked at it and we think we know the answer is 9. So if I take the integral of this, then that would be, well, notice this part doesn't change. It's still negative 1/12 x cubed. But x squared divided by 2, that becomes 5/4 x squared, doesn't it? And then this is minus 4x, and I'm evaluating it from 8 to 2. So since I have that sitting in my calculator from a second ago, all I have to do is make some minor modifications to it. Four, 4 times 8 squared minus 4 times 8 minus 4 times 8. I got 5 1/3 when I put 8 in. Now I'm going to go back and put 2 in. I got negative 3 2/3. Okay.
You got 9.
I got 9. So that has to work if you think about it, just because of the properties of calculus. But again, just like Justin reminded us, it's sort of troublesome because this is not the same area. It's the same size. But if we graph both of those equations, they aren't going to look the same, but it works. And so that's a little bit of a time saver. Now, in some respects, I'd say more is lost by the time you saved than by just doing them separately, if you will. But you know, we are just going to subtract these. But also, if you go back and think about the picture, why does this work? Kind of a visual reason why this would also have to work. Aren't we just finding the sum of a bunch of rectangles every time? Like that's all we're doing, right? But my question to you is, what do those rectangles look like in this picture that I see isn't showing up for you guys yet? Oh gosh. Wow. I have a picture of the graph sitting there for you to look at, and it's just not there yet. Must be because these pictures take time to upload or something.
So are you Zoom through your computer and then doing stuff on your iPad is what you're,
I just have I tried connecting my iPad directly to my computer this time, instead of the way it was last time, and it really isn't making any difference. I'm going to give you a problem in just a second, and I'll shut my computer off and restart it, and maybe that'll make a difference. Wow. Come on. Can you see the blurry graph in the background? I'm not sure if
doing
you can see right now.
kinda?
There we go. Like we're trying to find that area, but aren't we? This really isn't any different than before. So I just drew 3 rectangles in there that I guess will show up in 20 minutes or so. But the rectangles don't go all the way down to the x-axis, right? They just go from the red curve down to the blue curve. Well, how tall are those rectangles? How would you describe how tall they are?
Not very.
Well, I mean, mathematically, they're still narrow. Remember, they're infinitely narrow, but because they don't go from the red curve all the way down to the x-axis, they go from the red curve. Hey, look, they're showing up now. This is very exciting. It's like Christmas. How tall are those rectangles? How would you describe how?
Does it vary?
Yeah, notice they're all different. So you can't just say they're 9. Like they get taller to about where I have that middle one. That's probably maybe the tallest one, and then they start getting shorter again. Now I'm going to stupidly write something else that takes forever. Isn't the top of that green rectangle kind of like y1, or isn't that a y coordinate to get to the top of that? And then to get to the blue one, isn't that like y2? Isn't that the y coordinate of each of those? So doesn't it make sense that these heights right here would be the y height of one minus the y height of the other? I mean, isn't that what we just did? You see what I'm saying? You see why it has to work, like to kind of do the shortcut?
Yeah, I see what you're saying.
Hey, it showed up. Collectively, it makes sense that we can actually subtract them. So you don't have to go all the way down to the x-axis. You can just say, well, it's no different than before. It's like, how wide are my rectangles? Dx. How tall are my rectangles? Well, now they're not just a y value. They're the y value of 1 minus the y value of the other. Do you see the logic in that? So it makes total sense. It sort of has to work, right?
Yeah, because y1 is essentially f of x, or f1 of x, and y2 is f2 of x. So
That's exactly right. Okay, so I'm going to give you another problem, kind of entirely from scratch, and get you started on it. I'm going to go away and come back. See how long it takes this to show up. So this time I'm going to give you 2 parabolas, one facing downward, and I'm going to say it out loud since it's not going to show up for a minute. Negative x squared plus 3x plus 7. So that's a downward parabola. Negative x squared plus 3x plus 7. It's a downward parabola. And so in the real world, that doesn't make sense. You have to give boundaries to it. So that's kind of my upper boundary since it's facing down. My lower boundary that I'll call y2, I guess, is an upwards parabola. Like it doesn't have to be a line. It could be a parabola going up and a parabola going down. It's very exciting. So the second parabola is y equals 2x squared minus 9x minus 8. And notice I didn't tell you where these run into each other. Second one is 2x squared minus 9x minus 8. I didn't tell you where these run into each other. So you got to Desmos it, or maybe even do the algebra to figure out where they cross each other. And it's kind of cool that you can do this. And I probably will this time. I'll probably do this without cheating. I'm going to wait till the second equation shows up before I go away. So there's your two equations. Can you find the area defined by those two curves, or the area that's encased by those two curves?
Well, without Desmos, you have to start with the quadratic to get your 2x intercepts.
Exactly.
Those two.
And you also have to know which one is which, in the sense that which one is top and which one is bottom. In this case, because one is negative, it sort of looks like that'll be the top, but you sort of have to graph them a little bit. If you got it backwards, you just get a negative area. Like in our last problem, the area was 9. If you got it screwed up, you'd get -9. Like there's no such thing as a negative area. It just means you subtracted wrong. You don't even have to start over. Just say, oops, must have subtracted the wrong way. The answer is 9. So I'm going away. I'll be back in a second. Let's see, can I go away? Yeah, I think I can go away, can't I, if I just shut my computer down?
Yeah, we'll still all be here, I believe. It's one of the students to the.
Let's see. I guess I'm just going to hope you don't go away.
Before you leave, Doug,
Yeah.
I just graphed this on Desmos, and never mind, it should work. Just the answer will be negative.
So am I wrong? Do I not have the right one that's on the top? I mean, I was just guessing because I thought, oh, one's this way, so I'm probably defined it.
No, it should work, I think.